Today we're looking at section 12.1, which is the definition of a derivative. So one of the classical problems in mathematics has always been the way to find the tangent line to a given curve. So we call this the tangent problem, and the tangent problem was how to find the tangent line to a given curve. Now recall back in geometry, a tangent line is a line that hits the curve in exactly one point. So along came the concept of the derivative, and that was the solution to the tangent problem. So this is the derivative is just the culmination of the concept that was the solution to the tangent problem. So what happened is mathematicians started looking at a graph. Oh, before we go on that, we'll go ahead and let you know the derivative is one of the major concepts of calculus, the other one being the integral. So the two major concepts is derivative, which will start now, and then we also have later on the integral. So looking at a graph, what we discovered, if we pick a point Q and we picked another point on the same graph, such as P, and we got that slope, that's fine. However, it's not a very accurate slope of that curve because you have all of this gap in between here. So we said, okay, well, let's pick a point closer to Q. And we did that. So again, we've got some gap. Then we picked a little bit closer, and then a little bit closer. And you keep getting closer and closer and closer. And what happens is that the slope kept decreasing, so it's approaching a number. However, it's never going to, it's not going to keep decreasing. Eventually, it's going to reach a limit, okay? So it's going to stop at a point called the limit. So does the slope keep decreasing? No. Eventually, it's going to hit a point and not go past that, and we call that a limit, right? So no, stops at a point. The limit, which is great because we've been studying limits, so we can use the definition of limit to help us find the tangent line to a given curve. So let's say that we have 2 points on our graph. We have x, f of x, so xy, and then we have x plus h, and then f of x plus h. So basically, we're saying take your x and add a little bit, and then whatever y results from that, right? Because f of x is the same as y when you have x. So f of x plus h is what do you have whenever you plug in x plus h. Okay, so we've got 2 points on a graph, and h represents the difference in the x values, right? Because we started with x and then we just added a little bit, some unknown value, okay? And if we were to think about the slope, which again, remember, we're trying to find the slope of this tangent line, right? We can use the formula for slope, which is the change in y over the change in x, or y2 minus y1 over x2 minus x1. Well, if I were to label these 2 points, x1, y1, x2, y2, and then plug them into my slope formula, I would have f of x plus h minus f of x over x plus h minus x, which would then simplify to f of x plus h minus f of x over h. Okay, which is fantastic. Okay, so now we have the slope of the curve, okay, or slope of that line between those 2 points. So we find that the slope of the tangent line is then the limit of m, okay, as our second point gets closer and closer to our first point. So in other words, as x plus h decreases approaching x, we can express it in the terms of h approaching 0. So we can get a limit, all right? So we get the limit as h approaches 0. Okay, so as the change between your 2 points gets smaller and smaller and smaller, it's going to approach something, and that approach is the limit, right, which is why we're taking the limit. And we call that the derivative, okay? So the word derivative actually refers to two different things. It refers to the slope of the tangent line at a point, and it also refers to the slope function. So for example, when we're talking about the slope of the tangent line at a point, we would say the derivative of f of a means that you have the slope of the tangent line at x equals a. All right, so let's look at some definitions for this lesson. So we've got two definitions of the derivative, okay? The first one is the slope of the line tangent to the function f or g or h or whatever you're naming your function for a given value of x So in symbols, it would be the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, if the limit exists. The second definition of the derivative is the function. So first definition is the slope of the line, so you'll get a number. The second definition is you might not get a number, but you might get a function. So this is the function that represents the derivative for each value of x. Okay, and the derivative function is denoted in these symbols. It'll either look like f apostrophe of x, right? Sometimes we say f prime, okay? Or we might see this dy dx, which is a dy over a dx. So that's how it's denoted, okay? So we would have something like f prime of x, which is the same as dy dx, which is the same as the limit as h approaches 0 of f of x plus h minus f of x over h. All right, so the change symbol, okay? The change symbol corresponds to the letter D, okay, and stands for difference. Okay, so the change in x or y. And the D, so similarly, the D in dy dx stands for differential. So difference, differential. That is the limit of the difference. The limit of the change. So you know that the change in y over the change in x is a ratio, right? That's how we get slope. However, the dy dx, even though it looks like a ratio and it sometimes behaves as a fraction, it is not, okay? It's not a ratio, but rather it's a limit of a ratio. So it's a limit of a ratio. So it's not a ratio itself, but it's a limit of a ratio. So the derivative can be denoted several ways. We already mentioned a few. One of them was using the prime, okay? We also have, since f of x is the same as y, sometimes we say y prime, okay? Then we have the dy dx. Okay, so again, since y stands for f of x, we sometimes will write this, d dx f of x, okay? And since f of x means y, we can also do this, d dx y, okay? So those are all denotions for the derivative. So let's do an example. Let's say we want to find the derivative if f of x equals 3x plus 5. So first things first, let's just go ahead and state the definition of a derivative, which is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Step 2, we're going to substitute for f of x plus h and f of x because we know what f of x is. F of x is 3x plus 5. So anywhere that I see f of x, I can write 3x plus 5. And if I have f of x plus h, that's saying substitute x plus h for x, which I can also do. So I'm going to have, instead of having 3x plus 5, I'm going to have 3x plus h plus 5. And then I have minus f of x, so minus 3x plus 5, and then all over h. All right, so now we do some simplification. So this right here is equal to the limit as h approaches 0. I'll drop my 0 there. And I'm going to distribute this 3. So I've got 3x plus 3h plus 5. Distributed this minus 3x minus 5 all over h. So that is equal to, well, this 3x minus this 3x, and then I've got this 5 minus this 5. So on top, I'm just left with 3h over h, okay? The h's simplify, okay? That means that I now have 3. So step 3 is finding the limit. So it's saying, go ahead and plug in 0 for h. Well, the h went away. It's canceled, which means that my limit is 3. All right, and then that is how you do a problem like that. So I just found the slope of the line tangent to the function 3x plus 5. So let's look at another example. So I have find, oh, this kind of got cut off, f prime of x if f of x is equal to 1/4 x squared. So first thing I'm going to do is state my definition of f prime of x. So remember, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Substitute for f of x plus h and f of x. So again, I'm going to take x plus h and substitute it in for the x. So instead of saying 1/4 x squared, I'm going to say 1/4. I'm going to substitute x plus h for the x. So x plus h squared. And then I still have, then I have minus f of x. So minus, and then f of x was 1/4 x squared. And it's all over 0. And I still have the limit as x approaches 0 in front because I haven't evaluated my limit yet. Not x approaches 0, h approaches 0. All right, so now I need to simplify this rational expression. So first thing, let's go ahead and square that x plus h. So we're going to get the limit as h approaches 0 of 1/4, and the x plus h squared becomes x squared plus 2xh plus h squared minus 1/4 x squared all over h. Okay. So from here, I can go ahead and factor out the 1/4. Okay. And then also I have an x squared minus an x squared, which means that will cancel, okay, leaving me the limit as h approaches 0. Remember, I pulled a 1/4 out. So on top, the x squared got subtracted over here. So now I'm left with 2xh plus h squared all over h. Ooh, there's 2, I could factor out an h here as well. Let's go ahead and do that. So now I have the limit as h approaches 0 of 1/4 h, 2x plus h over h. These h's cancel. So now I have the limit as h approaches 0 of 1/4 2x plus h. All right, so here I can apply the scalar limit theorem and go ahead and substitute my 0 for h. So I have 1/4 2x plus 0, which means that I get 2x, 1/4, 2 of x. So 1/4 of 2 is 1/2, which means I get 1/2 x. Okay, so as you notice, this is not a number. I didn't get a number, which is okay because the slope of a tangent line doesn't necessarily, if we look back at our definitions, okay, the definition of 1 is just the slope of the line tangent to a function, okay, but we can also get the function that represents the derivative for each value of x. So if we think about it, this is a function, so we can actually find the value for any x. And so in other words, if we wanted to look at x equals 1, then we would just plug in 1 for x. So the slope of a tangent line can be a variable quantity. So we can actually look at a specific point. So one more example, we have find f of x, or f prime of x, if f of x equals x to the 1/2, and they actually told us for all x's between 0 and positive infinity, which tells us that we're probably going to end up with a variable quantity, which is fine. So step 1, we want to state the definition of the derivative and substitute into it. So remember, we have the limit as h approaches 0. We first need to do f of x plus h. Okay, so I'm going to plug in x plus h for x. Remember or recall that x to the 1/2 is the same as the square root of x. So we're going to have, remember, we're plugging in x plus h for x. So I get x plus h. Then minus f of x. So minus the square root of x all over h. From here, what we want to do is we want to rationalize the numerator. So that way we can eliminate our h. Because our h causes a problem. We can't plug in 0 for h if it's by itself in its denominator. So we're going to rationalize. So remember, to rationalize, we can multiply by the conjugate. So that means I'm going to take my problem, and I want to multiply numerator and denominator by the conjugate of that numerator. So I'm going to multiply by the square root of x plus h plus the square root of x. That's the conjugate of the numerator. So do that on top and bottom. All right, so from here, in my numerator, I get, go ahead and write out our limit, because we haven't evaluated yet. The square root of x plus h times the square root of x plus h gives me x plus h. So I've got this times this and this times this, which cancels, whole point of rationalizing. And then I get minus the square root of x times the square root of x, which gives me minus x. So that's what I have in my numerator. And in my denominator, I have h times the square root of x plus h plus the square root of x. Okay. So from here, the x's cancel, leaving me h in the numerator. And because I have an h in the numerator and then I have an h here, that's the reason I didn't distribute this h, because if you notice, this will cancel with this, leaving me 1 in my numerator and the square root of x plus h plus the square root of x in my denominator. So now, if I find my limit by substitution and I plug in 0 for h, what I will have is I will have 1 over the square root of x plus the square root of x, which is 2 square roots of x. So this is finding my limit right here. I substituted 0 for h. And then from here, because our problem started with a rational exponent instead of starting it as the square root of x, we can actually change our answer back into rational exponents. So remember, the square root of x is actually x to the 1/2. So I'd have 1 over 2 to the x to the, it's going to be 1/2. All right, and if I want it to, if I want my variable to be my numerator, I can move him to my numerator by making my exponent negative, and then we'll just leave this 1/2 out in front. And we have found our limit. All right, go ahead and try some problems on your own.